Welcome back from our long absence. We've been gone almost a week, and I'm completely lost. But hopefully now, Group B is ready for lab number 4, which is today. Hopefully you have already started and maybe completed homework number 11, which is also due today. Group A's lab number 4 report is due tomorrow, and their pre-lab then for lab number 5, Group A, is due this Saturday. You get an extra 50 minutes to work on that pre-lab on Friday. You will not have class in this class this Friday, the 15th. What we want to do today, what I want to do, I don't know if you want to do it or not, but I want to finish up Chapter 8, which is the RLC circuits, and in particular today we will be looking at series RLC circuits. We went through parallel RLC circuits before. There is a slight difference in the polynomial that results from series RLC circuits and parallel, and essentially alpha changes. That's the big thing. But the structures of our solutions are the same, and that's what we want to look at. We'll look at developing or coming up with the differential equation. Then we'll convince ourselves or remind ourselves of where R is going when it now becomes completely oscillatory, this RLC series circuit. Its behavior is maybe different than the parallel in terms of what R does. Then we will actually go ahead and compute R to find a critically damped circuit, and we'll look at some limiting values of currents and voltages and some circuits given time. Here's our circuit that we are playing with now. This is a series RLC circuit, and let's go ahead and just put the forcing function in there, because we know that if we do this, we could always set V sub s equal to 0 to get our natural response. That's our homogeneous solution. If this is what we are looking at, this circuit, what are you anticipating for the order? What's the order of the differential equation generically for a circuit like this? What are you expecting your resulting differential equation? If this one differential equation describes the dynamic behavior of this circuit, what do you expect that differential equation's order to be? Second order. We have two energy storage elements, L and C, so we should be anticipating a second order differential equation since we have two energy storage elements. With those elements being L and C. What variables do we want to focus on? If we're now trying to find governing equations that govern the dynamics of this circuit, what variables are we sort of clued in to thinking about or thinking we need to be focusing on when we're writing these equations? And if you need any help, you can just, it's starting to get a little bit colder. And so now you say, okay, Eli the Iceman, does that help? Does that help us at all figure out what variables we need to focus on? Here we know from Eli that the inductor's voltage is proportional to the time rate of change of current through that inductor, or L di sub L dt. And that now says that this derivative, or this differential, now clues us into what we're interested in. Now we need to focus on the inductor current, because that's going to be continuous. ICE tells us additional information. ICE says that the capacitor's current is proportional, and the proportionality constant is the capacitance C. It's proportional to the time rate of change of the voltage across that capacitor. This now says, if we are thinking the same way as we did before, now we need to focus on capacitor voltage. Bottom line, when you're looking at a circuit that contains L's and C's, you might be thinking inductor currents, capacitor voltages in trying to describe its behavior. Now that we know we want, or we're interested in, inductor current and capacitor voltage, so what? Well, now what do we do? How does that help us? Well, we could be thinking, we could say, well, here's the capacitor voltage, here's the inductor current. Does that help? How would you like to analyze this? Or what's your favorite way of analyzing a circuit? Does that give you a clue? That's probably most people's favorite. Here we have a mesh. Let's just write a KVL equation and try to see what happens when we keep track of the inductor current and the capacitor voltage. We'll start at the lower left. We now have minus V sub S plus the voltage dropped across that resistor using the passive sign convention is R times I. I'll not yet subscript any of these variables. I'll wait. And then we have the voltage dropped across that inductor. Can we describe that in these focusing variables? That's Eli, that's L di dt. That comes for us. What about the capacitor? Well, that's V sub C, is what we said. So let's write all that down. We now are trying to write the governing equations. We're writing a KVL equation, and we said that's minus V sub S plus Ri plus L di dt plus V sub C, and that's equal to 0. Now we actually have I sub L and V sub C both in that equation. Can one be substituted away? Can we get rid of one of those so that we end up with one equation with the forcing function V sub S? V sub S is a constant. Everything else is time varying. R, L, and C are time invariant. Those are constant parameters. What's common in this series RLC circuit relative to the elements? What connects all of those? What do they share? Share the same current. So let's note that the series current is shared by all elements. And that says then, well, I sub C of t is from ice C dV sub C dt, but I sub C is the same as all the other i's. That's I of L, I of t, because of this series circuit, or the fact that all of these elements are in series. Because of that, let's now use this relationship. Let's now use C, dVc dt. Everywhere we see an I, let's substitute it or replace it with C, dV sub C dt. That now allows us to rewrite that KVL equation as minus V sub S plus Ri, but I is being replaced with C, dV sub C dt, plus L di. Again, I is being replaced by C dV sub C dt, so now we need to differentiate that a second time, and we have our capacitor voltage as before. And now we have a second order differential equation in terms of the capacitor voltage V sub C. Or now we can write that as LC second derivative, or I'm going to save space or ink and just say double prime for the second derivative with respect to time, plus RC V sub C prime of t plus V sub C of t is equal to V of S, V sub S. Or you might want to normalize the highest power of the, or the coefficient of the highest derivative in that expression by dividing through by LC, and we now have V sub C double prime is now equal to, or plus, R over L V sub C prime plus 1 over LC and this now is our standard second order differential equation for a series RLC circuit. And that looks a little different than what we ended up with a parallel RLC circuit. Question? So this is only the case for this structure of a circuit. We have one effective inductor, one effective capacitor. If we had two capacitors in parallel and they could be combined into an equivalent capacitor, you could now say effectively I have one capacitor. Likewise with the inductor, you could have two inductors either in parallel or series, and you could create an effective inductor. But if it all boils down to this, that's what we're saying our second order differential equation is describing, is L effective, C effective, and R effective in this series mesh. That's what we now have used to end up with this second order differential equation. What's the structure of V sub C of t? Well, we can do the same thing that we've done before. We can say, well, let's assume that it's exponential with the coefficient a and this complex exponential s. Let's let V sub C equal a e to the st. In this homogeneous equation, we're now setting V sub s equal to 0, and we get something similar. We differentiate V sub C once with respect to t, and that s pops out. We get an as e to the st. We differentiate it again, and we get an as squared e to the st. This in blue is what happens when we assume this structure for our solution, And now we say, okay, we want to find a non-trivial solution to that. Well, we can actually identify a common factor, a e to the st. Factoring out what's left, we end up with s squared plus r over ls plus 1 over lc. And that's the characteristic polynomial when set equal to 0 gives us our characteristic equation for the series RLC circuit. What's different? The coefficient associated with the linear term s. What was it before for the parallel? Do you remember? Instead of r over l, it was RC, 1 over RC. But that's the only difference. But now we have a different relationship between these three parameters, R, L, and C, when they come in a series package or if they come in a parallel circuit package. That's the only distinction. And this is a second order quadratic equation, so we can get three different possible solutions or structures based on the e to the st, depending on what those values of R, L, and C are. Overdamped, we have two real unequal values of S sub 1 and S sub 2 based on R, L, and C. Critically damped, what's that look like? When we know that our circuit is producing or yielding a critically damped response, what do we know the structure of that solution looks like? Has real and equal. And that means we have to make the a e to the st independent, and to do that we introduce a coefficient t in front. We introduce powers of t to give us linearly independent modes for that repeated root at S sub 1. The other possibility introduces shaking. Now we have complex conjugate poles. Complex conjugate roots. I'm using terms that you'll get to at least in 320A if we don't get to them here. But here we just refer to those as the roots of our characteristic polynomial in the characteristic equation, and that's S sub 1, S sub 2 at minus alpha plus and minus j omega sub d. Omega sub d is the imaginary component of our roots. That gives us the oscillating piece. The alpha, and here I should say that's e to the minus alpha t, and e to the minus alpha t in the other term. They're exponentially damped at the same rate, and alpha is now r over 2l instead of 1 over 2rc. This is now the alpha for a series. RLC circuit. The natural frequency, omega naught, is the same. And if we want to relate or find omega sub d, I like to just invoke the Pythagorean theorem. Here's our S-plane. We know we have roots that are complex conjugate. Let's just focus on the one in the upper half of the S-plane. The distance it is away from the origin is actually its natural frequency. That's the hypotenuse. That's omega sub 0. its real part, how far it is into the left half plane, that distance is alpha. The omega sub d, how it oscillates, is the damped frequency omega sub d, where this root is now minus alpha plus j omega sub d. And we can now find omega sub d from the Pythagorean theorem. We know alpha squared, the real part squared, plus the imaginary part squared must equal the hypotenuse squared. We can solve that for omega sub d squared. And we want omega sub d. We now just take the square root of that. And that's the formula or the expression that you might see in the book, but instead of trying to worry about memorizing that, you can just think about the graphical connection and say, oh, I have a real part and an imaginary part when I have complex conjugate roots. The real part is alpha. The imaginary part is the damped frequency omega sub d. And the distance that root is away from the origin is the natural frequency omega sub 0. And in this case, if the natural frequency, if L and C stay the same, you're always the same distance away from the origin. You could now reduce the damping, make alpha smaller and smaller, and where does that x approach, or where does it go as alpha gets smaller? It's going to the y-axis. It's going to the purely imaginary value. And that's when we have our tank circuit. We now have a true oscillator. We have no more damping to dissipate any energy. We're just sitting there oscillating at the natural frequency omega sub 0, which is 1 over the square root of LC. That now naturally leads us into when is there no damping in a series RLC circuit? Or can we make this become a tank circuit? When will the inductor and capacitor just start sharing or transferring the energy of each of what they contain back and forth? When will the electric field or the energy stored in the electric field be pushed over to the energy stored in the magnetic field and then pushed back, etc.? We know we have this. This is now our characteristic equation. And we could think of this many different ways. We could say, okay, we don't want any damping. Or we're trying to make this look like, what's our tank circuit look like? That's our tank circuit. Can we create that from the circuit on the left? Just let R go to 0. That now becomes a wire. If we let R go to 0 here, we now end up with purely imaginary roots. We have S squared plus 1 over LC equaling 0. Or, let me write that down. We now have S squared plus 1 over LC is equal to 0. We now have S squared is equal to minus 1 over LC. We now are taking the square root of a minus, so that gives us a J, and we want plus or minus J, 1 over the square root of LC, or if it seems better, you can just say that, the square root of 1 over LC. In what was no damping in our parallel RLC circuit? I'm not trying to confuse you, I'm just wanting you to make the contrast. The parallel RLC circuit, all of these three elements were in parallel, R, L, and C. How did we remove damping? How did we make the damping go to 0 to get a tank circuit? To get this red circuit with a parallel RLC, what did we do with R? We removed it, which was effectively saying make it go to infinity. In the series, to get the tank circuit, we need the damping or the resistance to go to 0. They're dual. One goes one extreme, one goes to the other extreme, but we end up with both of them giving us a tank circuit. Let's now go back to our series RLC, and let's say that we now have a 1 Henry inductor, a 1 farad capacitor, and I want to actually select an R that will give me critical damping. We know the roots. The roots are minus alpha plus and minus the square root of alpha squared minus omega naught squared. Alpha is R over 2L in this series RLC structure. Omega naught squared is 1 over LC. What are we trying to do? We want critical damping, which means we want two real equal roots, which we're really saying we need to force this argument underneath the radical. We want that to be 0. And then we'll get two real roots, both of them at minus alpha. Doing that says we need to set alpha squared equal to omega naught squared. And we already have formulas for alpha. We have formulas for omega naught. If we now take the square root of both sides, or maybe before we do that, let's just plug in some numerical values. We assumed L was 1 and C was 1. Now the square root will be easy to find. We're just taking the square root of 1, which is 1, or we now know that we have R over 2L is equal to 1. Or R is equal to 2L. L was 1. R needs to be 2 in order for our circuit, this series RLC circuit with an inductor of 1 and a capacitor of 1, unit-wise, says, oh, if we now had R equal to 2, we would end up with the roots of that characteristic equation being at minus alpha, which is minus R over 2L, which is minus, and we have two of those, so however you want to write it, minus 1 for S sub 1 and minus 1 for S sub 2, but we have two of those to deal with. Now, in solving these types of circuits, we're going to need to get comfortable finding our initial conditions. So let's do that. Let's look at a circuit. Say that we have the following. Suppose we have a switch here's C, and let's say this is 2 microfarads. Let's say this is now example 1. This L, let's say, is 5 millihenries. R, let's say, is 2 ohms. And we'll say that this switch opens at 0, and we have a source that's constant of 10 volts. And we're trying to now find the inductor current at time 0 plus and the capacitor voltage at time 0 plus. How do we approach that problem? The circuit's been in a constant condition prior to t equals 0. That switch has been closed a long time prior to it being opened at t equals 0. That now establishes initial conditions. What does this circuit look like for t less than 0? Can you now redraw that circuit? We have our source, have our resistor. What's the inductor look like? Due with constant sources, that inductor behaves like a wire now. What about the capacitor? It opens up. And now we have this configuration. We have I sub L of 0 minus, and here is V sub C of 0 minus. I wanted them at 0 plus. But what do we know about inductor current and capacitor voltage? Eli and ice, those are the ones that get differentiated. Inductor current, capacitor voltage, they have to be continuous. They can't change instantaneously. So whatever they are at 0 minus, they are at 0 plus. What is I sub L of 0 minus? Five. No. How much current is flowing? 0. There's no current flowing. So I sub L, so the answer, if it was multiple choice and I said 5, that's kind of trying to lead you to quickly, yeah, that's 5. Quickly circle it and go on. So just be cautious. I sub L of 0 minus is 0 amps. There's no current flowing. What's V sub C of 0 minus? 0. There's nothing there. Can we write a KVL equation? We can always write a KVL equation. We can write KCL equation. What if we write a KVL equation? We now say minus 10 plus 2I plus V sub C of 0 minus is equal to 0. And you just told me what I was. Now we know what V sub C of 0 minus is. It's 10 volts. It's the voltage that source has across it. That's what the capacitor is now charged up to. Now we know the answers. Now we know, because the inductor current is continuous, I sub L of 0 plus, 0 amps. Capacitor voltage is continuous, V sub C of 0 plus, 10 volts. Let's do another one. 2. I like 2, so let's give R equal to 2. It's not my favorite number, but you wouldn't know that necessarily. I'm sorry, I'm just drawing. I need something, because I need to distract myself from the drawing. The drawing is terrible, but it's a circuit. Ooh, that does look pretty bad. That didn't do any better. Let's just quit. Here's 3. Oh, you know what? I wanted another resistor there. 5. And let's not get too creative. Let's keep that at 2 microfarads, and this is 5 millihenries. And let's say this is opening at 0. And we want to know, oh, that capacitor in the manufacturing process was a little off alignment, wasn't it? Well, hopefully it still works. The leads are a little out of alignment. Needs the chiropractor or something maybe. Straighten it up. All right. What do we do now? We want to find the inductor current at time 0 plus and the capacitor voltage at time 0 plus. Well, last time we tried drawing that circuit for t less than 0 before the switch opens. Let's do the same. Let's look at this when t is less than 0. We have our source. Now I get a second chance. We have our resistor. We have another resistor. What's the inductor do for a constant source? It's a short or a wire, so we can just replace it with a wire. What's our capacitor do? It opens up, and now we have 2 ohms, 3 ohms, 5 ohms. Aren't you glad you learned the first few chapters of the book? Resistive circuits. That's all we're doing now to try to find these initial conditions. What's I sub L of 0 minus? Nathan wants to write 2 mesh equations, I know. But the second one is easy, isn't it? What's the second mesh current? It's 0. There's no current flowing in that second partially connected mesh. It's not even a complete mesh. We really just have the one mesh, the one loop. We can now say this is 10 over so now we know I sub L of 0 plus. What about V sub C of 0 minus? It was 10 last time. Is it 10 now? Somebody thinks I can see 30 feet. But yes, your hand signals, I think I'm reading correctly. How do we find V sub C of 0 minus? You can find it many different ways. You've already found the current flowing through all of our resistors. It's flowing through the 3 ohm. That's the only resistor that the capacitor is seeing in terms of charging it up. So whatever that voltage drop across that resistor is the capacitor's voltage. Or you could say it's a voltage divider. However you want to do it, V sub C of 0 minus is now, let's do the voltage divider. 6 volts. It's not 10 because that capacitor doesn't see all of the supply's voltage. That supply voltage gets divided among the 2 ohm resistor and the 3 ohm resistor, and the only piece that the capacitor sees is the voltage dropped across the 3 ohm resistor. So now we know V sub C of 0 plus. You see how you can just, now if you need to pass time, if you're waiting for your food at a restaurant, you just grab a napkin and your felt tip pen and you just start analyzing circuits. Wait staff will come over and go, we don't offer that. You can say, well, I want that on the side. Right? The omega, we're going to get there tomorrow with sinusoidal steady state. But now let's talk about what is the response structure. First, let me just say we're playing with this circuit. And what's the key word now? Series or parallel? Series. So now we're using that characteristic equation that we've derived for the series circuit. Suppose we want to know what is the response structure when R is equal to 1, L is equal to 1, and C is equal to 1. I was numerically challenged today. I'm just sticking with ones. 1, 1, 1. What's alpha? Series RLC circuit. You could rederive it. You could actually find the characteristic polynomial by plugging in the structure and analyzing it. But if you remember, you're dealing with a series and you go, oh, alpha is R over 2L. It's a second order. These formulas are for that purpose and that purpose only. We plug in the ones and we end up with alpha being 1/2. What's the hypotenuse? I'm sorry, what's the natural frequency? That wasn't a slip, actually. I'm wanting you to start thinking about where these things are located in the complex plane. How far away is this set of roots to our characteristic equation from the origin? Aren't you glad I was numerically challenged? Square root of 1. Don't you wish your exam was today? Somebody wanted to cancel class today. Yeah. You'll wish it. No, never mind. The exam was better this time. Okay, the results. Omega naught is 1. So we're 1 away from the origin. What kind of a structure do we have? If we drew this, why do I draw? I can't. But now we're 1 away from the origin. Our damping is 1/2. How do we determine what structure we have? We're usually comparing alpha squared and omega naught squared. What's alpha squared? Omega naught squared. Which one is, now I feel like I'm at Sesame Street, which is bigger than the other? One of these things is not like the other. One of these things is smaller. That's not quite what they did at Sesame Street, I don't think. Didn't they celebrate an anniversary, Sesame Street, recently? Didn't I see that? 1/4 is less than 1. What does that mean? Does that tell us anything? We now know that this distance is alpha of 1/2. This distance is 1. And we can now find the opposite side of this right triangle. That's omega sub d. Omega sub d is the square root of 1 squared minus alpha squared or this is now the square root of 3/4 or the square root of 3/2. About 0.86. What's our structure for the solution? And now I could ask on the exam, is it overdamped, critically damped, underdamped, or none of the above? Where's the x? Is it on the real line? Or I could say, is it oscillatory, purely oscillatory? Where would that x need to be if it was purely oscillatory? No damping, right on the vertical. It has only vertical or imaginary component, omega naught. This now has complex conjugate. It's now underdamped. What's the structure? Or where are our poles? It's minus 1/2 plus and minus j square root of 3/2. So now we know the structure would be b1 e to the minus 1/2 t cosine. What do we now do? How are we shaking? What's the frequency? Is it omega naught, which is 1? Do you see how you could cook up answers for a multiple choice? Is that the right argument? No, it's the damped frequency. That was DAMP, ED, damped frequency, which is somebody's falling asleep watching Sesame Street. How fast is this going to decay? When will this no longer be visible? How do I like to describe this? This is an exponentially damped sinusoidal response. We have something shaking. We know what it's shaking at. It has an exponential envelope within which it's shaking. When does that exponential envelope decay to nearly, or when do we say it's effectively reached its final value? 5 time constants. What's the time constant here? So now if we said, when is this response going to be gone? We would say, oh, gone in 5 tau. Well, what's tau? Well, tau is determined when we look at the exponent. 1/2 t, and we replace t with tau, and we set that equal to 1. Tau is 2 in this case. Our time constant is 2. So now we wouldn't need to worry about this after 10 units of time. So now infinity is 10 seconds. Everybody still have their napkin? Look at different values of r on a couple of napkins. Look at r equal to 2 and r equal to the square root of 10 and see what kind of responses you get. So now I'm suggesting you say, suppose r is 2 and r is equal to the square root of 10, and see if that results in more or less damping, whether you now have overdamped, underdamped, or critically damped for those sets of r's, with L and C being the same. We'll pick up in Chapter 9, our last chapter, tomorrow, which is sinusoidal steady state.